Let's talk about sigma notation. So this notation we're going to be using a lot for the rest of the semester. You may have seen it before. This may be your very first time. So this video is just to make sure everybody's kind of on the same page with this, this letter here. So this symbol right here is sigma. So sigma notation uses this guy. It's a Greek letter, and we use it because it's the Greek letter S, and we use it S for sum. So we're using this symbol to represent the sum of a bunch of expressions, so things that are being added together. So when we do sigma notation, you can kind of already see our first example waiting down here. This is the general form that you're going to see. You'll have the sigma. You'll have, to the right of it, some sort of formula with, our first few examples will have a K as the letter, but really the letter can be whatever you want it to be. But it's some like formula of K, right? So if you look down here, we've got K squared, K over K plus 1, some sort of formula. And then on the bottom here, you have K equals some number, and then some other number up here. So this A and B that I have in red, you can see in this first example, they're 1 and 3 respectively. Those are your start and stop K values. So this is your first K value, and then this is your last one. So this means, okay, do f of this number plus f of the next plus f of the next and go all the way up until you hit this number, then stop adding. So what's kind of implied here is that k is always an integer. So what you'll see here for these numbers is always integers. So we're talking like 1, 2, 3, 4, 5, never a fraction, never, pi or anything like that. And at least in this class, we're going to see it's just 0 and up. So when we see k equals 1 and the 3 on top here, that's telling us that k is going to start at 1, then go to 2, then go to 3, and then stop because 3 is our max. And that's generally how sigma notation works. It's kind of excessive for a small sum, but if you're using it to represent a really large sum of things that have a pattern, it actually saves you a ton of space. Okay, so let's do this first example here. I would say this out loud: the sum from k equals 1 to 3 of k squared. Okay, so if k equals 1, we'd have 1 squared, and then we add. The next k value is 2, so we get 2 squared. The next one is 3 squared, and then I'm going to stop there because this is telling me 3 is the max value. Right, so 1 plus 4 plus 9, that's something I can actually just compute. 1 plus 4 plus 9 is 14, so this sum is equal to the number 14. Right, so I'm going to do this next example. If at any point you feel like you're kind of getting it, feel free to pause me and try the example and then press play to see the answer. Okay, so for this next sum here, we have the sum from k equals 0 to 5 of k over k plus 1. So here we have k in 2 different places in the formula. So when I plug in 0, 0 goes in both of those spots as my first number. This, of course, will simplify to 0 in a minute, but whatever. Okay, so my next k value is 1. My next k value is 2. And then 3, and then 4, and then 5. And we stop at 5 because 5 is my top number here. Oops. Okay, so if we're actually going to compute what this number is, this is definitely a lot more complicated than the one before it, but we can at least kind of simplify it a little bit. We've got 0 plus 1 over 2 plus 2 over 3. And you start to kind of see this little pattern come out where you have consecutive numbers. If you do add these all up, you could make one giant common denominator, or you can throw it right in a calculator and it should come up to 3.55. Okay, so my next two examples are a little bit different, just to kind of show you where this is headed. So this first example here that's coming up, instead of using k, I've used an I, and literally everything is exactly the same. It's just I want to show you, like, you'll see this with different letters. K and I and N are all really common. but really this works with any letter as long as you just indicate what that letter is, you know, in these two spots. Okay, so this one we have the sum from I equals 3 to 5 of 1 over I. So now I'm plugging in I equals 3, I equals 4, and I equals 5. I didn't pre-compute this one, but this is just some number, you know, works the same way with an I as opposed to a K or an N, which we'll see a lot of. Okay, so my very last example here is very, very similar to the one before it. 1 over I and 1 over K, they're going to be producing the same, you know, it's the same formula, just with a different letter. So what's really weird here, my starting value is different, it's 1 instead of 3. But here, we have an infinity as the top number. What that is indicating is not so much that you're going to stop at infinity, because that's not really possible, because infinity is not a number, but it's really saying, you know, keep adding forever. So it's telling us that it's like an infinite sum, and that's what we're going to be calling a series from now on. And this will take us pretty much to the end of the semester, talking about series and how they work and how they connect to functions and so on. So the pattern would start the way that we're familiar with, right? So my first K value is 1, and then 2, and then 3. But now there's no place to stop. So at some point you have to say, like, plus, you know, continue this pattern forever. So you're not going to come to, you know, a final number, at least not in a really obvious way. Sometimes these do add up to something finite, but it's not going to be really obvious what it is. So what's really important is that we put this dot, dot, dot at the end to say this pattern continues forever. Now, what's interesting, I picked this example in particular. This is called, oh my gosh, I'm blanking on the name. Oh no.